Okay, so the cry is an ontology, right? Um, mine God. So what is this? This is a simulation, particle simulation, where we have like 100,000 particles running around and living. And I can zoom in, and you can see that all of them are kind of moving. And it's easy to spot a pattern of the green ones, right? And it looks like Sierpinski triangle or like a fractal. If you're a computer scientist, then you'll know that this is like a basic shit 101, because I've also been accused of that. And I'm working with basic shit 101. So this is one of the most favorite basic shits 101 that I have, which is, let me just zoom out of this. There's like 100,000 little dudes here. None of them know about this world, really. All of them have some world in their mind, and if you put a lot of them through this world, like with that idea that, oh, I have a word in my mind, and if you put like 33,000 of them, then you get to see them. Now let me hide two of those gases. So this is clearly, there's a map that these dudes have in mind, and they move across, and the map essentially tells them where they can move or where they cannot move. But the map is not this. There's no texture here that tells anyone, hey, this is like, right? There's no texture. There's the compass only, and I can steer that compass. Right? You'll see that they change. This is cool. Now I need to, I think, do one more thing so that we see better what is going on, right? So this is what the green ones are thinking this world looks like. And what is this shape and pattern? Well, it's or. And then you can ask, what or? This is XOR. This is OR, right? We can change it. And look, I could say a word or two here about things, but I don't know what anybody knows, so I'd rather answer their questions. But I'll tell you this. This world is 1024 by 1024 pixels big, which is 2 to the 10th, if I'm not mistaken. Now, here we have 12 as bits, and you'll see if I but let's use a different, let's use XOR here. So, or maybe even, yeah, XOR is good. So I'll change that, and you'll see as I go lower on the resolution, you start to see more and more of an actual pattern on lower bits. And this is 1-bit XOR map, and I'll show you 1-bit XOR map looks like this. And you would think, hey, this is like, okay, like we gave them a texture, and like they cannot move here, they can move here, or maybe there are some different rules about moving here, you know, because there are distinct groups here. And if I increase the depth to 2 bits, just as I increase the depth to 2 bits here, you can see. And there are different ways of calculating the result of the operation between 2-bit sequences, right? And you can do that with like more bits, and you can see the pattern. Essentially, you can think of either it increasing density by without decreasing size, or it increases size because right now we're fitting it, right? Like we're fitting it to the screen. But look, 2 bits, 3 bits, 4 bits, 5 bits, 6 bits. Now, you can do all of that in brute force by just calculating, because it's like a multiplication table or matrix, right? And you can do that brute force for like 7 bits and 8 bits and 9 bits and whatnot, right? They grow massively in size by the time you kind of reach. So, like, you can actually view a 64-bit map, which is huge, huge, 2 by 64 and 2 by 64. It's a lot. It's a lot. And you can view it because we are not keeping it in memory, because no memory here on this computer. Okay, this computer doesn't have enough memory to hold 2 by 64 by 2 by 64. And this is essentially a map of every single thing that a 64-bit CPU processor, computing processor unit can do, essentially. This is like a genome or like a brain map of the 64-bit CPU, we think. In any way, we have a way, a method, an algorithm to create those for any number of bits, for any of the 16 operations that are available in 2 dimensions. But also, we have an algorithm for thanks. We have an algorithm for n dimensions. Like, I'm showing 2 dimensions here because 2 dimensions is easy to show, but we also have 3 dimensions. Like, let me check. That'll be the easiest way, probably. Upmap 3D, yeah. So this is the same thing in 3D. Right? Now, it's increasingly more difficult to view those things for people on a computer because, you know, you gotta color points, and there's a lot of points in it, right? There's a lot of points, even on like, okay, right? So at some point, your computer will just fail to show them all, but it calculates all of them quite quickly, right? Like, it's not 60 frames per second now, it's 64 bits, but this is bigger than some parts of the universe. But the point is, we don't keep that as a stored information, pre-calculated information that I keep in my brain about where shit is. No. No. Each of those little fellas here, right? Each of those little fellas is essentially every time he is somewhere, that algorithm, that calculation tells him, hey, it's red, and your neighbors are blue, green, red, because those colors are essentially voltages, okay? Voltages, they're electronics. Electronics. Now, right, so here, for example, if you XOR 0 and 0, you get 0. If you XOR 1 and 0, you get 1. If you XOR 0 and 1, you get 1. If you XOR 1 and 1, you get 0. And if you sum the zeros and ones in a binary sequence, and you count ones as +1 and 0 as -1, then you get charged movement across this map, because you can have different algorithms for a point on a map and its neighbors, and any kind of a sense that you want to give it. Because like your body is just your sensors that are close to you, but your eye can actually see, far away. So maybe you can kind of get calculations for that whole line and that whole line and that whole line and that whole line, and we can sell it and we can tell it, hey, in bioelectromorphology, Dr. Michael Levin says that your cells, essentially don't know what they are from like any absolute value of anything, but they know what they are and what they should be doing by the relative differences between them and their neighbors when it comes to voltage. So I believe this is partially at least the model, because we can say, hey, if you're here, your next move is the lowest, like the move that would cost you the lowest amount of change. So if you're blue, you tend to stay within that blue period unless we tell you, hey, you're like a not cross-dresser, but like but cross-dresser might be okay. Like you like to get on red from time to time, and that's okay. Because here, our behavior is here, right? So it looks for absolute minimum voltage, not relative to my, right? This is some other way of doing this. This is the same as the first one, but it just we called it quantum because we give it like 20% chance of like not giving a fuck about any walls. So you get more, like this is more rigid, as you can see, and you can see the grid that they're kind of avoiding and moving, the probabilities of where they will be. And this is like, yeah, but walls, what are walls and borders? And this is the Dr. Michael Levin kind of idea, which is I sense myself, I sense my neighbors, and I see the differences between us, and I go to the neighbor which is the least different than I. And on top of that, because this is just pure electronic based movement, like I'm here, I didn't do anything to get here, but I'm here now, so I get an emotional feeling of where I am, and I'm like, it's cool. And I look at my neighbors and I see that this neighbor is very similar to me and he likes beer and football, so I'm going over there. But we both don't know where the hell we are. And we can move about none the wiser. Like I don't have to know where everything in the universe is if I can just go there and see what's there, right? And that's the system that we occupy, kind of, I think. Now, if somebody now says and thinks, hey, the world doesn't move, like, it doesn't feel like, it's not as gritty, as rigid as this. And I'm like, yeah, sure. When you zoom into the world, like, it becomes a grid because at some point you'll reach the Planck length. So it is grid, it is digital, if Planck was right. And if not, then what are we doing even? It's also kind of interesting point. But if you increase the depth, you see, you increase the depth of the idea of what they have in mind as the world, then at some point, and not too far away point, because this is depth 7 only, right? Depth 8, depth 9, depth 10. Let's go with 28. So in their mind, all of them have a space that is like 2 by 28, like 2 to the 28th by 2 to the 28th big, and it's a XOR map. So I can tell you exactly, like 28 bits, XOR map. This is what they have in mind when they move about on it, right? So if we change it to like OR, you can see that it's mostly red, but it's not really red. Like if you zoom into it, like you'll see that, hey, it's, there are places where there's quite a lot of not red, and they are kind of far in between. And if you think, well, how is it that, because here, this is like a lot of information about how to move it, right? How to move. And just look at how big this part is as I zoom out. Right, so it's this there, It's this there. Have you seen? Have you remember it? Have you seen it? Okay, we're zooming out. It was somewhere there. I swear to God, she was there. Anyways, so this is cool, right? Now you can see. Oh, they're kind of like, this is the grid that they occupy. But the thing right now is that none of them feel or sense any other green dude, right? So even though they look as if they're working together because they're, organized in a way, that organization doesn't come from any of them knowing where is any of them, or know, like, they don't even know that what is this, like this space 1,000 by. Nobody has that in mind, okay? None of those green fellas, green berets. So how do you give sense to them and make group behavior simulations or predatory simulations or like cohabitants? Well, there's the DNA, which is 100% weight here, and the 100% weight tells me that 100% weight of my movement is according to the DNA, and the DNA is that map that they have in mind, right? Which is like a little bit of code that takes your X and Y and tells you your voltage. And you can take that a little bit of code, which is your compass, and you can change the X and Y from your position to like X plus 1, Y plus 1, and it's like your surroundings. And then you can give them, hey, you can have that compass on a stick. And we call that like either sixth sense or like far sight or like long hair that inform you, hey, oh, I touched the screen. So now we'll give them senses. Or maybe I can even like remove their DNA from their mind. And you see, none of them now remembers that they had like an op map to move around, and it's noise. All right? So let's give them 10% of like DNA, and well, it's 10%. But it's really like 100% because we have two things that fight for the weight. It's the DNA and the surroundings, right? So let's see if it works out of the box. Yep, it works. So now what they're doing is no DNA, and they're kind of mixing together, right? Okay, no DNA. So this is pure noise. Now we'll make them like each other, because here's one. So green likes green, right? And it's yet another type of noise. But then we'll add the DNA as well. So we have like equal part DNA and equal part the weight of, their being there. Now I need it. And now we make them dance with each other, although still keeping the map in mind, right? So now it's a completely different little world. I remove DNA. I remove the senses of self. I add the DNA. Now, if it's fractal, if it's like different DNA, right? You see the immediate change. And then I can add this like movement around. And now you have ants that build Sierpinski triangles. And if you ever ask yourself, how do ants build Sierpinski triangles? It's like the triangles are already there and ants are just moving, because what are they gonna do? What are they gonna do? Now, funny thing, number last is, let's take the red one and let's have it on, right? Now the red one has something in mind, and it's a different thing in mind because it's XOR at 10-bit. Like, let's do it XOR at 7-bit, right? So now you can see we can have multiple beings, because we have red beings and 33,000 of them, and green beings, 33,000 of them. And both of those beings have different worlds in their mind, and they think effectively that the world looks different. And the world is essentially, where can I be and where can I not be? And they occupy the same space. None of them know that this is the space that they're occupying because they don't have a senses about that space. They just kind of get the information of what's up. How are you? How am I? How are you? And we can also give those red boys a sense of self, and they like reds, right? But we can tell them, hey boys, you can sense yourself and you dislike yourself. And you can see what that makes, what that does to a being, right? Now they don't like each other. I mean red. Now we'll make red like each other. Now we'll make red indifferent to each other. And it all changes how they behave. But we can also make red like green, if they sense it, right? And we can make the red forget the DNA exists. And that's cool. And we can make green forget DNA exists for a night or something. So when it comes to movement of those things, we're not doing random movement like the physics department love to do, but what we're doing is essentially the only random thing is the placement of the boys here, right? The only random thing is that we randomly place those. Once they die and we reborn them, we randomly place them, but their movement isn't random. Their movement is totally deterministic, although really, really hard to predict. Now, we can spawn the bit in one place instead of all places at once, and you see how that works, right? For the green, they're kind of swarming around them, and we can move the green here, and we can paint with the light that we're kind of, and we can make green dislike, or make it like red, and dislike green, like more, like red more than it likes green, and we can give it the DNA, right? So it kind of does that, and we can make it senseless to the surroundings, so it's mostly like yeah, so that's cool. Now red, I would like you to chill out, worms, and like get rigid. Right, so now green, da 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 do 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 do. And one more thing is that there's a certain directionality to all 16 of the operations. Not this one. So as you can see, if you treat this as like map of movement, you can feel, okay, this is free movement, right? This is no movement at all, or vice versa. Now this for the electronics is like, we'll move this way, right? And you can see this if I change the red one to not XOR, but like, oh yeah, this one, right? You see, see this. So this would be probably, which one? This one, right? Cool. There are 16 operations, and all of them, as you can see, point towards some corner or are lines. Or in the case of XOR is like, XOR is the, as you can see, the most orderly chaos looking thing. Like the most fair. Because XOR is fair. Because XOR will give you something. Like if you have a pair. If both people want to do the same thing, XOR will not make them do it. But if one of them does that and the other says, I'm not doing it, like XOR will allow that to happen. Like XOR is anti-greed. Because if you're greedy and I'm greedy, XOR will give us nothing. But if you're greedy and I'm like, you can have it, you will have it. So yeah. And this runs on a processor. This, all of those 100,000 particles right now, nothing is being calculated on GPU other than like, how do I paint it on a computer? But this is not GPU computation. This is CPU computation. So imagine this on a GPU, if you can. Because when it comes to, well, what is GPU capable of? It's capable of drawing these. Like, this is not 100,000 particles running at 60 frames per second. This is, well, at the moment, 1.5 million running 60 frames per second, and we can also like do all kinds of shit with it, like electrogravity, right, with the GPU. So it's, things are coming. 26 minute, God.